So today we're going to start a new topic, which maybe will continue for the next, two or so lectures. And this, might be of interest to many of you, which is really applications of randomization to machine learning. And I want to talk about a classic problem called the experts problem. And this really, I want to sort of emphasize sort of the power of randomization. The power of randomization in prediction. And I'm going to start with sort of a vanilla, easy to understand setting. And especially, because we talk about Bernoulli's a lot, let's just think of a binary prediction problem. And the prediction problem is, every day we need to predict just a Boolean. For example, is it going to rain? Or, if you prefer, is, stock X going up? Or, will we see more than X traffic on a website today? There are various questions you could just frame as a Boolean, like you just need to predict, is a particular event going to happen or not? Now, the problem is, let's just say that we're doing rain and, you're not a meteorologist, you have no idea how to predict, but what you have are access to n experts. So there are n experts who make predictions. And the question is, who to follow? So note that this is unlike a typical algorithmic setting where you think of a well-defined input and an output. It's an online setting. So it's an online setting. So the way to think of this, excuse me, is on day t, here's what happens. So you have these experts. And I'll refer to these experts as E1 up to En. There are n experts. Each of them make a prediction. So they make a prediction for day t. These will make a prediction, and this will be. Let me just say that this is the prediction of expert 1. This is the prediction of expert 2. This is the prediction of expert n. For simplicity, we can just think of the prediction is a Boolean. Excuse me. Is it going to rain? Is it not going to rain? So on and so forth. So all of these predictions would go into the algorithm that you build. So the algorithm will take all of these predictions. It will use these predictions to actually give its choice at time t. So I will refer to that as x sub t. This is the prediction of the algorithm at time t. And then the truth is revealed, and the truth could be, either it rains, or I guess it doesn't rain. So one of these options will appear, right? So either xt, the prediction, is correct, or is wrong. And if the prediction is wrong, then the algorithm incurs a penalty. And this penalty is often referred to as a loss. And then this process will happen the next day. Now the algorithm stores some state. So the algorithm has, you can think of it as it has some state, right? So it's storing some data structure. And based on the prediction, the algorithm updates data. So the algorithm incurs the penalty, the algorithm updates the data structure, and then the process continues. Right? So
when you say when you say the process continues, you get the predictions from the experts once more.
Once more, yeah, exactly.
Okay.
So the entire, this entire scheme. So it is at the beginning of each day, each expert makes her prediction. The algorithm will take those predictions, take some state, right? So it has a data structure that is storing some history. Maybe that history is the performance of all the experts so far, right? So at this point, we are not considering, even though the algorithms that we give are going to be efficient both in space and time, we are not considering the size of the data structure nor the running time, for now. Because we have an even harder problem, which is what is the guarantee? So the experts are going to make their predictions. The algorithm is going to combine those predictions to make its own prediction. The prediction is going to be either correct or wrong, depending on which the algorithm incurs a penalty or a loss. We'll call it the loss. And the loss could be really simple. So let's just keep a very, very simple loss here. And then, in general, in machine learning, you can do more complex versions of losses. The loss at time t, right? The loss at time t is simply 0 if the prediction is correct, and 1 if the prediction was wrong. And we can do fancier versions where maybe you're trying to predict a real number between 0 and 1, and then you have some version of loss, which could be maybe the absolute value, the square of the absolute value. And of course, these will start changing the character of what's happening. But for now, it's just simplest to assume that there is some loss, and the loss is just Boolean. Right? So to me, this is sort of the easiest setting of the expert's problem. Yes, question.
So the loss would then apply to the prediction which was incorrect by the specific expert, or it could be multiple of cases, right, where multiple experts are incorrect.
Right, but in some sense, the loss is not incurred by the experts. The loss is incurred by the algorithm. The algorithm is using the experts. So in some sense, the algorithm is on the hook to predict. So when the algorithm makes a mistake, the algorithm incurs a loss. Now one can interpret that as a loss of a particular expert, which we will be doing, but that is not central to the problem formulation. Right? So think of it as the job of the algorithm is to predict whether it rains or not. And it pays a loss for every mistake it makes. Does that sort of answer the question?
Yeah, thanks.
So any other questions about the setting? So it's important that you understand, there's sort of this, there's an order in which things happen. So the order is first predictions. So let me just sort of write this down. First, the experts make predictions. Then the algorithm makes a prediction. Right? So the algorithm uses the experts' predictions to make its own prediction. Finally, we can say, we'll say like the truth is revealed. The algorithm incurs a loss, and then the algorithm does an update of the data structure. And sort of this happens, for all time steps. So for all time steps, these, I like to think, you'll see that when the algorithms are discussed, a lot of these steps are combined into one step. But conceptually, I like to think of it as these sort of distinct steps. The experts make their prediction. The algorithm is going to look at those predictions, combine them in some way, and make its own prediction. And again, to keep things simple, we will assume that the predictions are Boolean. Like you have to say 0 or 1. The truth is then revealed. And the truth is, was the prediction correct or wrong? Depending on that, the algorithm incurs a loss, but the loss could be 0. Finally, the algorithm does an update of its data structure based on what happened, which presumably the algorithm is going to look at all the experts, see the loss they incurred, and maybe penalize them, maybe do something, and then decide what to do the next time around. So does the setting make sense? Any questions?
This might be a stupid question, but if instead of a binary prediction, we had, suppose the algorithm returned some probability of it raining,
Sure.
which is between 0 and 1, would the same setup make sense?
Sure. I mean, then instead of, it might be easier than to, okay, good. So this is a reason, the good question is, how do you generalize this? So you could think of the predictions, instead of being 0, 1, could actually themselves be in a range. They could actually be real numbers. In which case the algorithm itself is going to predict a real number, and the loss could then be a more complicated function of the prediction. Right? So this, in some sense, is really some function of xt, and you could imagine that this function goes from that range, and you can just rephrase everything. We can say all of this exactly as is, and of course it would define. The ability to learn would depend on this loss function, right? I mean, if the loss function was some kind of like a Dirac delta or something, then nothing is possible. But if the loss function is smooth, then you can start doing things.
Thank you.
Okay, but I want you to stick to thinking of the binary situation. And in general, I would also recommend that when you're looking at a lot of machine learning settings, it sometimes it clears up a lot of the air if you replace a lot of the real numbers by discrete quantities, and a lot of the underlying structure will start becoming clearer, because typically there's a lot of mixture of algebra and and an algorithm, and it's useful to sort of tweeze these apart so that you gain some understanding. And towards that, I want to discuss an algorithm for the experts problem, which is actually deterministic. And the reason is, I think by seeing the deterministic analysis, you will appreciate more the power of randomness. Okay, so so far so good. So what is sort of remarkable here is how to state the guarantee. How to state the guarantee. I mean, this seems kind of, it's sort of obvious in hindsight, but it is a little tricky, because if all the experts are bad, I mean, the algorithm has no hope, right? I mean, if the algorithm is trying to predict whether it's going to rain, and all the experts are randomly guessing, then how is the algorithm going to do anything better than just randomly guessing? Right? So we need to find some way of describing a guarantee that accounts for this fact. But what we'd like to say is, if there exists a good expert, the algorithm should find that expert. Or at the very least, the algorithm should incur small loss.
If there's like a really bad expert who always predicts incorrectly, can you like leverage that?
Who you mean? In some sense, if there is an expert, you mean who's always doing the opposite?
Yeah.
So to be able to account for that, you need to then start imposing some structure on the loss function. So what you're saying is, the having extremely small loss implies that actually they were making the opposite choice.
I guess all I'm saying is, like, if there's an expert that always predicts incorrectly, are we expecting the algorithm to be able to, like it seems like the algorithm should be able to say, like, okay, well, I'm just going to predict the opposite of that expert every time and always get it right.
So we are not going to give a guarantee like that, but that's an interesting point. In our case, we are not going to do that, and you'll see that because. So you'll see that the way I'm going to set things up, one can solve the issue that you're doing by basically, you can construct a fictitious expert who guesses the opposite of every expert.
Yeah.
Right? So now you have a bunch of experts, and then you want to follow the best one.
Yeah, that makes sense.
So typically in all of these settings, if you think that there is some variant of an expert which could also be considered, you would basically construct that variant as yet another expert. So your pool of experts is going to sort of expand, but we'll actually see that these algorithms are surprisingly robust to the size of the pool. I mean, there is a dependence, but the dependence is, it's only logarithmic. So you can easily, add in new experts of that form. Okay, so how are we going to sort of quantify this? So let me write out what I'll call the loss function. The loss function is, let's just say for now, it's the loss function is, so we discussed what the loss function is. It's just 0 if the prediction is correct, 1 if the prediction is wrong. But I just wanted to think of this as so, just saying that LT of I is the loss of the ith expert. So this is saying, suppose what you did was you simply predicted the ith expert every round. Then this is the loss that the algorithm incurs. Right? And I'm going to represent that as a function. Note that LT changes every single round, which is sort of the remarkable aspect of this. When you think about it mathematically, you're like, but LT is an arbitrary function. It can change arbitrary within these constraints. It changes every single round. How can one give any guarantee? So the total loss, so I'm going to sum t going from 1 to capital T. So capital T is going to be, sort of the final round. So T, this is the time horizon. So the total loss is just that, right? This is just the total loss of the ith expert. Now the loss of the best expert, and is L, which I will define as simply the min over all I. So look at all the experts. And that's what you want to get. This is the loss of the best expert. And so this is the benchmark that we're going to use. This is often also referred to as the optimal expert in hindsight. What this says is, suppose you knew, so you go back, you collect all the data that you've seen so far. Now you go all the way back and you say, okay, which expert was the best? And that would be a particular expert. And the question is, can the algorithm achieve loss comparable to L? So this is going to be the benchmark. This is going to be what we're trying to get. The optimal expert in hindsight is the benchmark. So the way to think of this is that if you knew all the past, you could obviously choose the best expert and just stick with that expert. But during the evolution of this process, the algorithm can switch between the experts. It can decide to predict with one expert or another expert or combine their views somewhat. And can this combination somehow be set so that at least the algorithm can achieve a loss that is comparable to the best expert? Now, the really nice thing about this formulation is, again, once one of the problems is, you read this so many times, you get used to it. But this is really brilliant. The fact that you phrase it in this term, because then you can start proving mathematical theorems. Because a priori, when you look at it, you say, well, you are assuming absolutely nothing about rain. You're assuming absolutely nothing about nature. You know that if the experts are random, then the algorithm should not be able to give a guarantee. So how do you sort of interpolate between situations where some expert is good versus all experts are bad? And the nice thing is you define a benchmark with respect to the best expert in hindsight. And you say, can the algorithm at least achieve that much loss? Okay, so does this setting make sense?
Obviously, like, the best you can do is better than that, right?
The best you can do is better than that. You could achieve loss 0 if you knew how nature behaved.
Or if, like, you had, like, one expert who is always right on Tuesdays and one expert who is always right on Mondays. And
sure. So there could
out.
be more sophisticated ways of combining the experts. And of course, a lot of research is on that.
Okay.
Like, can you beat this?
But basically, the algorithm is going to, like, figure out who the best expert is, and then all us guess what they guess.
Something like that. Or it'll figure out, like, a coalition of good experts.
Okay.
And even in situations where, like you said, maybe there's one expert on Tuesday, one expert on Monday, so on and so forth, you'll see that when you sort of trace down all of these arguments, they always do this, except maybe they're not going to define this over all time horizons, but some subset of the time horizons.
Okay.
So in some sense, this is really the core, and then everything else is sort of built on top of this. Like, one thing you might say is that, can I be comparable with the best expert every week and every month and every year, so on and so forth?
Yeah.
Or you could do it as, can I be compared with the best expert on Tuesdays and Mondays?
Sure.
Or so there are versions of this where, or you could imagine that there are certain experts who give predictions on certain days and don't predict on other days.
Yeah, like if an expert is right on every, like, on like random days, then there's no way to do as well as them.
Right, exactly, right? So the thing is,
when they're going to be right.
There is typically some structure in the expert behavior that you're then going to try to pull out.
Yeah.
But you'll see that this style of argument, which is to define the best expert in some subset of the time horizon, is sort of the main tool.
Okay.
Yeah.
So you say that we assume nothing about the truth or how nature works.
Yes.
But isn't that implicit in little l?
Of course, it is implicit in that, L is sort of implicit in little l. Yes, so little l is describing the behavior of nature. But my guarantee is with respect to capital L.
Okay,
so my point is that, okay, so obviously something has to depend on nature. So capital L depends on nature. But my point is, the theorem I'm going to state is not going to say if little l's have this behavior, then you can predict. It says no matter what little l is, you can always achieve the loss of the best expert.
I see. Got it. Thanks.
Because, if you really step back and think about it, it seems magical that you should be able to do anything when the algorithm actually knows, the algorithm in this case actually knows nothing. Right? The algorithm has no knowledge of nature. And so it's assuming that there is some expert who has some knowledge of nature. And it's trying to figure that out.
Sir?
Yes.
Another question I had was, you're talking about combinations of different experts. How would that happen since we only deal with discrete?
So you'll see.
Okay.
I will give you the algorithm and hopefully that will make it clear.
All right.
So I'm going to actually give you a deterministic algorithm. a deterministic algorithm. A deterministic algorithm, famous algorithm called weighted majority. We will show the guarantees of this, we'll see the proof, and then we'll sort of understand where is it that randomization can give us a win over the deterministic algorithm. Okay, so let me tell you what the data structure is, and the data structure happens to be very simple. So the data structure is just an array of weights. Weights for each expert. So what the algorithm is going to maintain is an array, which I will again think of as a function, is just a collection of in this case it's going to be non-negative weights. So at each time step, the algorithm is going to have a collection of weights, and we'll assume that W1 of I is 1, for all I. So initially all the weights are set to 1. Okay, so now let me give you the actual algorithm. So at time t, here's what the algorithm is going to do. Get predictions of all the experts. Okay, so I will refer to this as the prediction at time t for expert I. Right? So for all I, you have this prediction number. And remember, so each of these is just in 0, 1. Then compute the total weight of experts predicting 0, and then the total weight of experts predicting 1. Now it's called weighted majority is because the algorithm predicts the majority weight. This is badly phrased on my part, but hopefully you understand, right? It's going to compute the weight. It has a weight stored for each of the experts. And then it's going to look at, okay, so let me look at the total weight of predicting 0, the total weight of predicting 1, predict the one that's larger. Predict the majority weight or the larger weight. Right, the larger weight. Okay, so then at this point, now I'm going to sort of put this in a separate box. So then nature reveals the losses are incurred. Now here is the update. And this is important. For every expert I that is wrong, so for every expert that gets it wrong, we will update the weight for the next round. We'll say WT of I divided by 2. So for every expert that got it wrong, we'll halve their weight. And then the process continues. And this is called the weighted majority algorithm. So any questions about the algorithm?
So there's no like reward for someone getting it right?
There's no reward for getting it right. Well, the reward is their loss, their weight doesn't go down.
Okay.
Okay, very simple.
Is there any advantage to, or does it make a difference if we actually put a reward, because it will just be scaling down by a larger factor?
Yeah, it doesn't, because you could rescale everything. So you can think of it as what is not relevant is whether you reward someone or penalize someone, but rather the ratio of the penalty to the reward.
Yeah.
Right, and so the ratio in this case is 2, or half. Okay, so any questions about that? All right, so this is a deterministic algorithm, it's weighted majority. For the question of how does one do a combination, well, here's one way of combining experts. So you kind of side with the majority. You penalize the ones who get it wrong. So hopefully what's going to happen is that now note that if an expert was always correct, her weight will remain 1. And you are more likely to predict that expert. What is interesting here is that, let's say there was an expert who was correct half the time and another expert who was correct half the time. You may have to switch between them. And this algorithm automatically does it. Okay. So now let me state the main theorem. The loss of weighted majority, is at most, it's something like 2.5 times L plus O of log n. So it says that, let's say there was an expert who was correct 99% of the time, and let's say t was much larger than log n, then the algorithm will be correct something like 96% of the time, which is quite remarkable.
Could you remind me what n is?
N is the number of experts. So n is the number of experts, and L is the loss of the best expert. Now the problem with this proof is that the proof is short, but the proof is very magical. And once one digs into optimization theory, then sort of the magic can be somewhat demystified. But it's a potential argument, which typically I hate, because you have no idea how someone came up with the potential. So define a potential which is just the sum of the weights at time t. Okay. Now the proof really has 2 parts. So part 1 is to argue that every time the algorithm errors, the potential drops significantly. Part 2 is to say that if L, which is the loss of the best expert, is small, the potential cannot be too small. And then you combine them and say, hence, the algorithm cannot error too many times. So I'm sort of writing this out in English so that you'll see that a lot of the algebra will fall into one of these parts, or one of these, technically 3 parts. There's the combination step. So there's part 1, part 2, and then this I can think of as like you're combining them together. So we're going to define this potential. The potential is the sum of weights. We argue that every time the algorithm makes a mistake, the potential is going to drop significantly. On the other hand, we'll say that if L is small, so if there was an expert who had small loss, the potential cannot be too small. Another way of saying this is that we will lower bound the potential by a function of L. And then if we combine these arguments, we say, well, the algorithm cannot error too many times. Okay? So let's actually start with part 2, which turns out to be easier. So consider the best expert. The best expert, and say, let me call it I star. So what is the weight of I star at the final time step? Right? So remember that t was the time horizon, the final time step. And of course L is defined with respect to t. So this is exactly, note that, let's go back to this. Every time the expert made a mistake, her weight drops by half. So if the expert made a mistake L times, which is the loss of the expert, her weight is just going to be the initial weight divided by 2 to the L. The initial weights are all set to 1, and therefore the weight of that expert is simply 1 divided by 2 to the L. Then trivially, we'll just say the potential was just the sum of weights. All the weights are non-negative, right? And so therefore the final potential, I'll say Z of capital T is 2 to the L, because the weights are non-negative. Okay? So that's part 2. Now for the most interesting step, which is part 1. Suppose the algorithm made a mistake at time t. So that means at least half the weight, not half the experts, but rather half the weight, got it wrong. Right? If the algorithm made a mistake at a particular time step, because the algorithm always predicts with the majority weight, we know that half the weight got it wrong. And we are going to exploit this to show that the potential has to drop significantly. Okay? So let's write this as z to the t plus 1 is the sum over all the weights at time t. And I'm going to split the sum over the experts who got it wrong, plus the experts who got it right. These weights, okay? So this is exactly going to be the I who got it wrong of WTI by 2. Their weights dropped. But these got it correct. So their weight will not drop. Okay? Does everyone follow this step? Any questions about that? So I'm looking at the potential at time t plus 1. Split it into the ones who got it right, the ones who got it wrong. The ones who got it wrong, their weight dropped by a factor of 2. For the others, the weight didn't drop. The weight stays the same. Right? Now I'm just going to rewrite this as the summation over all I weights minus the summation over the I we got it wrong. So this is WTI divided by 2. Okay, so all I did was say that, I guess you can think of, I just sort of added, subtracted, both added and subtracted this quantity, right? So I simply added this to that to give the total weight, but then I subtracted this from this part to get the second term there. Okay. Now what is this? What is that quantity?
Just Z of t.
That's exactly just Z of t. What about the second one? How do we bound the second term?
So it's at least Z of t over 2.
It's at least Z of t over 2, or rather, without this is at least Z of t over 2, because it's half the weight, right? This is at least Z of t over 2, and therefore this is at least Z of t over 4. This is crucial. It is using this is where the weighted majority enters the picture, because half the weight got it wrong. Excuse me. Therefore, the sum of the wrong weights is at least half the weight, and so you get Z of t over 4. Putting this together, you can write this as 3 over 4 Z of t. Right? So what we have now is to say that whenever the algorithm makes a mistake, half the weight got it wrong. Therefore, in that time step, or rather, to the next time step, to the current time step, Z of t plus 1 is at most 3/4 of Z of t. There was a significant drop in the weight.
Wait, in the algorithm, we decrease the weights regardless of the algorithm getting it right or not.
That's right.
So why are we assuming that half the weight got it wrong here?
No, this is suppose the algorithm made a mistake at time t.
Okay.
So in time steps where the algorithm got it wrong, there is a significant drop.
Okay.
Does this make sense?
Yeah, that makes sense, yeah.
Now, simply the weights are non-increasing. Hence, for all time steps, I have a trivial bound. Okay, so let K denote the loss of the algorithm. Let K denote the loss of the algorithm. What we're saying is that Z of t is at most Z of 1 times 3 over 4 to the K. Right? Because every time the algorithm makes a mistake, it incurs 1 unit of loss. For that 1 unit of loss, the weight drops by a factor of, by 3 over 4. For all other time steps, we just apply the trivial bound. We say, well, the weight is not going to increase. Hence, we get this bound. Now, what is Z of 1? What is Z of 1?
Just n.
Is n. So n 3 over 4 to the k. Now we argued earlier that Z of t is greater than 1 over 2 to the L. Right? This was the part 2. And so we'll plug this in. And then we'll just take logs. All right? And so we get that L is, am I doing my math correct here? So let me just do this carefully. So L log half is at most log n plus k log 3 over 4. Mixing things around, setting it around, I'll get k is at most L let me see, make sure I'm doing this correct. Sure, right. Divided by log 4/3 plus log n divided by log 4/3. Okay. So any questions? Did you see how I got this? All I did was I just took the logs over here. I have the comparison between k and l. And you kind of, you write out what these numbers are. You'll get this is at most 2.5 L plus O of log n. It's better than 2.5. It's, I think, 2.4 is constant. Any questions? And I'll make it as a side note. I'm not going to say it's an exercise because it's a little involved, and you'll see that we're actually going to sort of do a similar version of this math. Is that there's no reason for me to set this to half. If I instead set it to WTI times 1 minus eta, where eta is a parameter, then you can get k is at most 2 plus eta L plus O of log n divided by eta. Where eta is a parameter. So parameter in 0, 1. So you can get arbitrarily close to 2 times L. Effectively what this is saying is we get as close, I'm just, this is an informal statement, as close to 2 times L plus some O of log n as possible. Okay? Note that you always incur some constant there. You're getting 2 times L, not 1 times L. You get 2 times L. So we get as close to 2 times L as possible. And no deterministic algorithm can beat a loss of 2 times L. Now I'm not going to write out the proof formally, but let me just describe the lower bound construction. So for any algorithm, for any deterministic algorithm, essentially think of experts and nature collude to force k to be large. How are they going to collude? And this is really, I want to emphasize this point because this is exactly where randomization can save us. So at every round, And actually, there are only going to be 2 experts in this entire thing, just 2 experts. So we'll set n is equal to 2. At every round, one expert predicts 1 and the other predicts 0. Just that's it. 2 experts. One expert is always going to predict 1. The other expert is always going to predict 0. Since the algorithm is deterministic, we can figure out, and we as in, let me say, nature, can figure out which expert the algorithm will follow. Or we can figure out the algorithm's prediction. Because it's deterministic, nature knows what the algorithm's prediction is, and what nature does is behave the opposite. So the algorithm loss is actually going to be t. But because one expert always predicts 1, the other expert always predicts 0, one of these experts is going to be correct half the time. So the best expert loss is going to be at least, is at most t over 2. So when the experts collude, the expert nature colludes, we can actually force the algorithm to make twice as many mistakes. Remarkably, we have an algorithm that gives you basically twice as many mistakes, even in the presence of any kind of collusion, and it's a deterministic algorithm. So in the presence of any kind of collusion amongst the experts and nature, nonetheless, we can get a factor 2, which I think is quite remarkable. So although there was no randomization here, the weighted majority algorithm is quite remarkable for its simplicity. So this is a good time for me to pause. I'll take any questions about what you have, and then I will talk about the randomized weighted majority algorithm, which can actually give you a 1 plus eta bound, and this is also considered as a low regret bound in machine learning terminology. So I'll pause the recording and I'll take any questions that you have. Okay, so now let me continue with the power of randomization. So remember, no deterministic algorithm can beat a loss of 2 times L. But with randomization, we are going to beat this. We are going to beat the 2 times L bound. And so let me give you this algorithm called randomized weighted majority. Randomized weighted majority. And again, as before, we maintain weights Wt of I. So at time step t, at time t. Now instead of combining the predictions based on majority, we will select an expert I proportional to the weight. So it's sort of like an importance sample. We follow the prediction of expert I. Right, so we just follow the prediction of the expert. So it's kind of interesting that when you frame it in this way, we don't actually even look at the predictions of the experts for that time step. Whereas in weighted majority, we sort of ask the experts, okay, what are you going to predict? But in this case, we don't even look at that. We don't even look at what their prediction is. So then we'll say after receiving loss, now we're going to do the update step. So we're going to follow the prediction. We will set the weight to be equal to whatever its weight was earlier. So now I'm going to sort of introduce some differences here. There is a parameter eta in 0, 1. This is referred to as the learning rate. This is referred to as the learning rate. We're going to decrease the weight by 1 minus eta for all the experts that are wrong. It is going to be convenient for me to say it in this form. So we raise it to the power of the loss. We raise it to the power of the loss. So let me sort of, so of course, this makes sense in the 0, 1 case, right? So for experts that got it correct, their loss is 0, their weight does not change. For experts that got it wrong, their loss is 1, and therefore the weight goes down by 1 minus eta. But in general, I actually don't even need to assume anything about that. I can actually phrase this quite abstractly by saying in each, I should say at each time t, after the expert, after the algorithm makes a prediction, nature reveals losses for each expert. So now we don't even have to think of it as Boolean. We can just think of nature is going to reveal this vector of losses where for each expert, nature reveals a loss. And then again, we want to be competitive with the lowest total loss. Right? So this is abstracting beyond the Boolean setting, which as someone had asked. So this is the update that I'm going to perform. You will often see this also expressed as follows. You'll see this, sometimes the loss is written in this form, and this you can see is like basically this is the first order Taylor, it's when you replace 1 minus eta by e to the minus eta, the first order Taylor approximation, then this is what you get. And therefore this is often also called a multiplicative weight. This is also referred to as multiplicative weights or the multiplicative weight update, so on and so forth, because we have a multiplicative weight. So this is a form that you will commonly see in a lot of theoretical machine learning papers. I'm going to write it in this form, but essentially the math turns out to be equivalent up to lower order terms. Okay, so does the algorithm make sense now? So instead of going by the majority, we select an expert proportional to their weight. We follow the prediction of that expert. We'll say, okay, we're just going to follow whatever that expert predicts. Now, nature reveals a loss for every expert. So the algorithm incurs the loss of the predicted expert, of the chosen expert, of the chosen expert. I should say follow prediction of the chosen expert. So there's no reason to put an I over there. And after receiving the loss, each expert, for each expert, the weight goes down by 1 minus eta to the power of the loss. Now this follows what we did for weighted majority. If LT of I was 0, then this is 1. If LT of I was 1, then we reduce by 1 minus eta factor. This is also alternately written as WTI e to the minus eta LTI. Okay? And the theorem, core theorem, is that the expected value of the loss of the algorithm is at most 1 plus eta times L plus O of log n divided by eta. So instead of the 2 plus eta, we get a 1 plus eta. The proof is essentially identical. We define the potential before, just as before. Well, it's identical modulo some algebra that we need to do, but essentially I should say the proof idea is identical. So we set this potential to be the sum of weights. So the part 2, as before, is z of t is at least wt of I star. Now what is wt of I star? It's wt of 1 minus eta to the power of the sum of Lt of I star, t going from 1 to capital T, and this is, remember, this is just 1. So this is just 1 minus eta to L. Right? This is what the final potential is, the lower bound of the final potential. Now let's do part 1. So let me just say that loss sub t is the loss of the algorithm at time t. So what is the expected value of the loss? This is the sum over all I and n, so we're looking at all experts, the probability that I is selected times the loss that the ith expert incurred. And note that these probabilities, the probability that I is selected is exactly that quantity times Lt of I, which I'm just going to rewrite over here as 1 divided by Ct, summation of I and n, Wt of I, Lt of I. Okay, so this is going to be an important expression for us to have. This is just saying that the expected loss is up to some normalization. We're basically looking at sort of some weighted loss where we weight by the weight of the expert. Right? That was the probability that the expert was selected. So this is the weighted loss, and of course it's normalized by the sum of weights. So hopefully nothing particularly magical here. So this is the expected loss. Now there isn't, instead of having this notion of what was the reduction of the potential when the algorithm was correct or wrong, because we have this more abstract setting where the algorithm is going to probably incur a loss every round, and it depends on what is the loss of the expert. Let us write this out. Let us write out the reduction. So what is the potential reduction at time t? The potential reduction at time t is z of t minus z of t plus 1. So we'll write this as Wt of I minus the sum over all of these experts as Wt of I 1 minus eta to the LT of I. I'm just writing out what these expressions are. I simply wrote this out as is. Okay. Now what we're going to do is so I look at that expression here. I'm going to lower bound it, therefore I can upper bound the potential reduction. Let me see if I'm getting this correct here. Yeah, okay, so let me write this as 1 minus eta LT of I. Okay. This is just using approximation times x. Okay. So what I have over here is that I can write out this difference in potential is at most the summation of I n n Wt of I minus summation of I n n Wt of I 1 minus eta Lt of I, and this leads to summation of I and n. Remember, these things cancel out. Wt of I, Lt of I. Okay. Now we've just seen this expression remarkably over here. So just so you can see it all together. This expression over here is precisely the expected loss times z of t. So this is eta times this potential times the expected loss at time t. Okay, now I will rearrange let me rearrange this. And what I would get over here is that z of t times 1 minus eta to the expected loss at time t. So I guess I've fudged my calculations around. What I wanted to do was actually to flip this. So I've made a mistake here, which sorry, just give me a second to fix the error here. What I need is actually, I need a lower bound on this. So I actually need a lower bound on this term, in which case I'd get this upper bound here. Sorry, so let me instead, my apologies for this, but let me instead just use this update as opposed to this update over here. Okay? And up to Taylor approximation, they're basically the same. And so the point is, in all of this, we'll have to do various Taylor approximations to keep things under control. It is going to be significantly more convenient. It will probably be more convenient for me to do this, although I don't know. I'm going to do the math and maybe I'm going to get stuck again. But let's use this update, in which case what we would get here is that z of t is greater than or equal to minus eta L, right? Because instead of 1 minus eta to the power, it's e to the minus eta to the power. In which case, what I would get over here, I'll get z of t minus z of t plus 1 is going to be equal to summation I in n wt of I minus summation I in n wt of I e to the minus eta lt of I. Okay? And so what I need is, I need a lower bound on this, so
You can expand it to order 2, right?
yeah, so I'll do a second order expansion over here. And so when I do the second order expansion here, I'll get wt of I 1 minus x plus x squared divided by 2. Not x, but right, 1 minus eta lti plus eta lti square divided by 2. And this is going to be equal to eta I in n wt of I lt of I minus eta squared by 2 summation I in n wt of I lt of I squared. Now this, as we argued, is just the expectation of the loss at time t times zt. lt of I squared. So this is going to be a bit of an annoying term, so let me see how to deal with that. But what you get is that the drop in potential is at least 1 minus the expected loss times zt minus some sort of a second order term. Minus a second order term. Okay, let me just rearrange that. So I'll write this out as z of t minus z of t plus 1 is at least eta times the expected loss at time t.
Could you move up the camera?
Oh, I'm sorry. Minus eta squared by 2 summation I going from 1 to n wt of I lt of I squared. And I'm going to move things around, I'll get one minus eta times that dy squared. So now I get that the potential, if the loss is large, the potential will drop significantly, right? Which is really the style of argument that I want to get. Now here I'll use this approximation.
That's a plus, right?
Sorry, that's a
Eta
plus.
squared.
No. It's a minus. It's a minus. It's a minus. Right? Because I did a second order
Yeah,
expansion.
you're right.
It's a minus there. Now I do a 1 minus x is at most e to the minus x, so I'll get dt exp to the minus eta times the loss at time t minus this sort of annoying term over here. So sorry, I'm blanking out a bit over here, which is
Right, I am actually a little bit confused about the sign because
Yeah, no, I think
z of t minus z of t plus 1.
yeah. So we start here. We go that is greater than or equal to. So this is correct.
Yeah, I think there's a mistake in this. Oh no. I guess this is right. Yeah, then it should be a plus. I guess.
Well, I just rewrote this expression here. I just rewrote whatever I had over here. Right, z of t minus z of t plus 1 is equal to.
Yeah, I think we're talking about the equation below that because we're
Here?
changing from sorry, no, like I agree with what's on the sheet of paper that's below this at the very top, but the
Oh,
right
I see. You
below
mean
that.
here there should be a plus. Yeah, you're right. Yeah, sorry. Yeah, you're right. You're right. Yeah, because I moved things around over here. Yeah. So we have this second order term. Which annoyingly, I think I fudged my notes somewhere, and so I ignored how to deal. I mean, I made some error in my calculations. So apologize. Suppose the second order term didn't exist, right? And I will try to patch this, and I will send some notes. So suppose second order term did not exist. I have to check exactly where my calculations went wrong. Well, then you get this expression. And then this works out perfectly as what we had earlier, that the final potential is equal to the initial potential in e to the minus eta times the expected total loss. And this, as we said earlier, we could bound No, I've made an error here, so this is not going to work. Sorry. So I have to figure out exactly where the second order calculation goes, because without the second order term, actually things don't work out.
So I mean, loss is bounded, right? LT of I is at most 1. And
Yeah, it is at most 1, but
so I have like eta square times something that resembles expected loss.
that's right. That is right. But then you don't get a multiple of ZT.
Oh yeah. Oh yeah.
So you need the ZT to be able to. Well, no, sorry. So
I'm still not
That's
sure why we
right.
actually need to do the second order expansion.
So actually, if you don't do the second order expansion, what you end up with is a theorem that's actually it's too strong. So so suppose you didn't. Let me show you what happens. So you'll get a bound of this form.
Yeah.
Okay, so this is going to be n times that. Now if you go ahead and take natural logs, you'll get that minus eta L is at most log n minus eta times the expected value of the loss. Now when you rearrange this, you'll get that the expected value of the loss is at most L plus log n divided by eta, which means if you set eta to be infinity, you'll actually get the loss. Of course, you can't set eta to be infinity, but you could set eta to be 1. Or you would set eta to be arbitrarily close to 1. So you would get actually exactly the loss plus log n, and that can't hold. And somehow the fact is that the fact that you're able to set eta to be large is problematic. So typically you want to set eta to be small. I don't know if that makes sense. So you need a second order term to actually get out the full balancing. So let me see if I think. Okay, let me see if I can if we can get this to work. LT of I is going to be at most 1, and therefore you can lower bound this by eta times, I think this is it, yeah. WT of I, LT of I, minus eta squared by 2, summation I and n, WT of I, LT of I. And then I think it works out. Okay, so instead of this, we'll go here. This will then give us what we want. We'll get eta times the expected loss at time t, zt, minus eta squared by 2 times the expected loss at time t times zt. This is what Akash had suggested, and so this is what we can do, right? So when LT is greater than 1, I can lower bound this as follows. Then I think I'll get what I want. Okay, so let me just do this afresh. So I'll get z of t minus z of t plus 1 is at least z of t eta times the expected loss at time t minus eta squared by 2 times the expected loss at time t. Then it's going to start working out. So then I get z of t plus 1 is at most z of t times 1 minus the expected loss at time t times eta minus eta squared by 2. Okay, and now I'll use the Taylor approximation. I'll say I'll get this is C of t e to the minus eta minus eta squared by 2 times the expected loss at time t. Putting it together, z of t is at most z of 1 times exponent of, this is the expected total loss, times this factor of eta minus eta squared divided by 2. And as we argued earlier, this is e to the minus, this was e to the minus, eta times the loss. Right, and this thing is n, and so taking logs, we'll get, this is log n minus eta minus eta squared divided by 2 times the expected loss. Moving things around, the expected loss is at most, and so this is sort of the divided by eta minus eta squared by 2 plus log n divided by eta minus eta squared by 2. This we can rewrite as 1 plus eta times L times log n divided by eta. So sorry for the error. I knew I fudged something in the second order term. So this is what we get, and this proves, I should say O of that, this theorem here. And this actually leads to a classic regret bound. So if eta is set to 1 divided by square root of t, then what you get is that the expected loss is at most, so that's just to balance out these two terms. So remember, you get a term like this, so it's L plus eta L plus log n divided by eta. Okay? And what you, log n divided by eta, so you want to balance these two terms out. So if you set eta to be 1 over square root t, because sort of t is an upper bound on the total loss, what you get is that the expected loss is L plus L divided by square root t plus log n times square root t. L is at most t, so what you get is, this is at most L plus essentially O of root t log n. Right, with a little bit more care, I could get that. So the idea is you take an upper bound on the loss, that's eta t, and you set these to be equal, eta, and you'll set eta to be square root of log n divided by t. So this is like the right learning rate that you want to set, and once you set this learning rate, you can get a bound of this form, and this is called the regret. So the regret is the expected loss minus best loss of expert, and the regret is essentially O of root t log n, and this is often referred to as sublinear regret, because the regret is little o of the total of the worst case upper bound. So this is sort of a classic result in the theory of machine learning, which is the expert's algorithm, and the weighted majority is an example where randomization can give you such a bound. So my apologies again on sort of messing up that second order calculation, but hopefully it's clear now. So what you do is, when you look at zt minus zt plus 1, you get this expression. You essentially apply a second order approximation to e to the minus eta LTI, and then you kind of go through the motions and go through the math and a bunch of things to crank out, but then what you get is a bound of the form 1 plus eta times L plus O of log n over eta. And when you set eta to be 1 over root t, or technically if you set eta to be root of log n over t, then what you can do is essentially you balance out these two terms. So there's this tension of, you want to set eta to be large to get rid of the additive term, but then that increases the multiplicative term. And you want to set eta to be small to improve the multiplicative approximation, but that gives you an additive approximation. You balance them out at this point, log n over t, where t is just a gross upper bound on L. There is a fair amount of theory on how to choose the optimal learning rate, because the optimal learning rate actually depends on L. And there's a lot of work on sort of trying to update the learning rate as you move along to get the best possible bound. But this was a discussion of the expert's algorithm, and next time maybe I'll continue with some other versions of randomization in these sorts of machine learning problems. So we'll end here, and I'll take any questions.